Good morning, good afternoon, good evening, depending upon where you're dialing in from. Thank you very much for joining us for Inflection's webinar, Quantum Technologies for National Resilience and Security. I'm Paul Lipman, Inflection's Chief Revenue Officer. I'm joined on the webinar today by Laura Thomas, an advisor of Inflection's and longtime national security and intelligence community professional. William Clark, Inflection's Vice President of Quantum Development for Defense. Max Perez, our Vice President and General Manager for Clocks. And Caitlin Conahan, our Vice President for Quantum Software. Today, we're going to talk a little bit about Inflection, provide an overview of the company and the markets we serve, some of the pressing national security threats that we see today and on the horizon, and then how quantum technology provides potential solutions to those threats. And we'll have plenty of time for Q&A. And if you have questions as we go through the webinar, please just enter them in the questions section of the Zoom application, and we'll endeavor to get to as many of your questions as possible. We look forward to them as well. So a bit about Inflection. We were founded in 2007 as Cold Quanta. We're coming up actually very soon on our 18th birthday, so a very exciting time for us here at the company. And we are pioneers in the neutral atom approach to quantum. We have technologies and products in both quantum sensing. We'll talk a lot about sensing in today's webinar. In quantum computing, you may recently have heard about our work developing logical qubit applications with our neutral atom quantum computer. And then quantum software, which not only force multiplies our quantum hardware, but provides a variety of end-user applications for processing and analyzing the data that comes out of these systems. We'll talk a lot about that. Caitlin will talk a lot about that on today's webinar. We got our start manufacturing technologies and components that are fundamental to the operation of neutral atom technologies for trapping, for cooling, and for manipulating atoms in their quantum states, and we use those in our own products. We also sell them to other participants in the quantum ecosystem around the world. And we're one of very few quantum companies that operates across AUKUS. As you'll hear, we have offices in the US, the UK, and Australia, and we're a long-time collaborator with the national security ecosystem in all three of those countries. Inflection is headquartered in Boulder, Colorado. That's where I'm speaking to you today from. Our quantum software operation is based in Chicago. Our advanced quantum testbed systems are in Madison, Wisconsin. We have a large presence in Oxford in the United Kingdom. We recently opened our office in Melbourne, Australia, and later this year, we will be deploying a very large neutral atom quantum computer in Japan under the Moonshot program. Uniquely, I believe, amongst quantum technology companies, we have quantum technology that is operating in space. We provided the core technology for NASA's Cold Atom Lab, which has been operating continuously in low Earth orbit on the space station for several years. And as you'll hear about in the webinar today, space is a really important part of the national security consideration set and the technologies that we're bringing to market and putting into these space-based platforms. We also collaborate with a large number of leading research universities, both here in the US and around the world. The vision of Inflection, quite simply, is to harness the power of quantum to expand human potential, and we do that across a range of industries and domains. We've recently done some very interesting work in life science, for example, in the energy sector. Today, we'll be focusing primarily on defense, and we'll be bringing solutions to these defense problems through executing our mission, which is to bring commercial products to market, to take quantum technology out of the lab, to productize it, to commercialize it, to deliver exponential performance improvements for our customers. And we'll talk about how we do that in a variety of domains in today's webinar. In terms of our product solution set, and we'll go through a number of these today, this ranges from Ticker, our optical atomic clock that provides orders of magnitude improvement in timing, precision, and resilience. SkyWire, our quantum radio frequency solution that really provides groundbreaking capabilities in RF spectrum awareness and utilization. Scale, our neutral atom quantum computer. SuperStack, our software platform for obtaining maximum performance out of quantum sensors and quantum computers, and then providing breakthrough capabilities for analyzing the resulting data. Caitlin will talk about that in quite some detail. And Exact, our quantum inertial sensing solution that has an important part to play in positioning, navigation, and timing, PNT, which will be an important part of today's discussion. Turning now to the national security threat landscape, there are a variety of areas, both as a function of today's geopolitical environment and technological changes, that are creating new kinds of threats that the Western world is having to address and deal with, and for where quantum has an important role to play. We'll start with some comments from a very recent Senate Armed Services Committee meeting, which are quoted here on the slide. The pace of technology innovation has fundamentally altered the battlefield. We'll talk about some of those technologies and the impact and implications. The Pentagon must use all available tools to improve the accuracy and agility of decision-making, and do that through access to better data. We'll talk about how quantum makes new kinds of data available and provides capabilities for making sense of that data and for analyzing that data that were not possible previously. And then comments from the next Defense Secretary that he intends to refocus resources on enabling our ability to prevail in conflict. And we'll talk about some of the ways in which that has to happen and some of the ways in which quantum has a part to play in bringing that to reality. First of all, though, we'll talk to one of the threats that's probably the most broadly known in the media, which is the threat of GPS denial. And we're seeing an increased amount of GPS spoofing, of GPS interference, of actually GPS denial happening in hotspots around the world. This is an image taken from a GPS map that shows interference with GPS in Eastern Europe just in the last week. This is happening in the Middle East. It's happening really now all around the world. And Laura, maybe I can bring you in here. Maybe you can talk a bit about what the impact of a GPS outage would be on the US and the ripple effects globally, and why the US government cares so much to wean themselves from this potential single point of failure.
Thanks, Paul. I mean, it's pretty simple to say, but hard to wrap our heads around. The fact is life as we know would be altered if GPS goes down. And you know, think about all the things that GPS forms the backbone for. I mean, many of our financial transactions, our communications, internet. Just you go to your bank account and you expect that when you hit refresh, a certain number is going to be there. And all of a sudden you can't see that anymore. I mean, that's what would happen if GPS goes out. And that's just on an individual level, but now magnify that, more broadly. And when you think about it from a national government perspective, logistics wins wars. And how does the military do its logistics? Well, it relies on GPS very, very heavily. So if we can't, have our battlefield awareness, appropriately in the right place because GPS has gone down, that's a real problem. Now, that's not to say that the military doesn't have, certain backup options, but it would be completely catastrophic. It is the bottom line if this goes out. And a lot of smart people are certainly thinking about it, but this represents the knowing doing gap that we often see in government. We know what the problem is, but doing something about it is incredibly difficult.
Thank you, Laura. I'll turn now and bring Max in to talk about how Ticker helps to address this very pressing problem.
Thanks, Paul. Yeah, the heart of every GPS, GNSS satellite system is a clock. Quantum provides the ability to make those clocks higher performance at lower cost and size so that the technology can be distributed amongst a wider variety of satellite systems. This provides a direct hedge against attack against our satellite systems. Some of our adversaries are known to have kinetic attackability, where they can actually destroy some of our assets that have been deployed. So distributing these new clock technologies in emerging government programs like resilient GPS provides our ability to get GPS, GNSS capabilities in the air faster and with improved capability over what is deployed today. Indirectly, quantum clocks can also be deployed in ground-based assets so that you can distribute time to both your defense or warfighters as well as civilian infrastructure. And we're working along both axes.
William, I'll bring you in to talk about how quantum radio frequency sensors can also assist in this area.
Yeah, thank you, Paul. GPS systems and our use of them depend heavily also on RF receivers that are used to multilaterate, to determine their position. And traditional receivers, which involve antennas and other components within the receivers, can be very susceptible to interference that is maybe just due to congestion in a given geographic area, or interference that may be intentional, aka jamming. Quantum RF receivers are unique in that they do not have antennas. These are small vapor cells filled with atomic gases, which are excited into states that are sensitive to electromagnetic signals. And so they exhibit a number of unique characteristics. In particular, they tend to be very linear, and that linearity means that we are able to better reject signals that would otherwise either degrade or deny performance in those types of environments under those circumstances. The other piece of it too is that these receivers can operate virtually anywhere in the electromagnetic spectrum, and so they can tune to support operation across multiple GNSS constellations, and also the ability in all PNT systems to use signals of opportunity, known signals in known locations that can be used for positioning purposes and therefore for navigation as well.
Thanks, William. And Caitlin, what role does software and particularly quantum software have to play here?
Yeah, thanks. So I'd like to start by contextualizing a little bit of the role that we play here at Inflection. So in our quantum software division, our core mission is to demonstrate the utility of quantum technology at the application layer, but also to enable state-of-the-art performance throughout the quantum computing stack. So our flagship quantum software product is indeed our industry-leading quantum software platform, SuperStack, which is designed to perform cross-layer optimization to amplify the performance of quantum applications on today's quantum computers. But today, what I would like to focus on is our division's focus on developing software layers that complement and leverage the capabilities of our next generation quantum sensing devices. And there's a number of ways that we do this, and I'm sure I'll be expanding on them as we go along. But one of the ways that we are supporting robust PNT in GPS-denied environments is through our Sapient framework, which I'm sure I will touch on in more detail. But what Sapient does essentially is leverage advanced multimodal learning techniques in order to integrate diverse data sources. So these could include your GPS signals, inertial navigation units, computer vision, basically anything that you have at your disposal in order to create a comprehensive model of the environment that is resilient to adversarial attacks. So you're really leveraging everything you have at your disposal and kind of tying it together in this sort of cohesive model to understand where you are.
Great, thank you. And Max, I'll bring you back to talk about the role of inertial sensing here.
Absolutely. Thanks, Paul. So Inflection has developed a suite of inertial sensing technologies based on quantum called Exact. Caitlin mentioned the Sapient program that's going on in quantum software, and that's a enabled system that allows us to switch between GPS or GNSS-based positioning and local-based positioning. And what Exact does when combined with our ticker clock technology is provide what's known as the full inertial basis to do navigation and positioning without access to any external signals. One of the challenges that's emerging in the space is our adversaries have access to tools where they can spoof the location by manipulating the GPS signals so that the warfighter on the ground or the civilian user of GPS doesn't actually know exactly where they are, and you can actually shift that position by manipulating the external signals. What Exact plus Ticker does is put on board a local absolute source of truth with respect to positioning. As long as you know where you started, you know where you are at. And again, utilizing Sapient, we're able to switch between global-based positioning systems and local-based positioning systems rapidly in the event that some adversary is manipulating the external signals. And this happens in two ways at Infleqtion. One is using inertial local onboard positioning systems, and the other is a program we have in gravitational based positioning systems, in which we understand the variations in the gravity profile in a location in order to use that as a point of reference.
Great, thank you all very much. That's very helpful. Moving now to talk about radio frequency spectrum awareness and utilization. Perhaps, William, I'll turn to you, as this is really your area of expertise, to talk a bit about the problem space and also Infleqtion's solution.
Thank you, Paul. Historically, and sort of alluded to also by earlier in this in our presentation here, every system out there, whether it's a logistics system or whether it is our communication and sensing systems, which are used for various operations across our various forces and in various domains. Historically, these have been stovepipe systems, and these stovepipe systems are inherently susceptible to a variety of attacks. In recent years, there's this concept of all domain architecture, one where there are standards in standardization interfaces, different types of waveforms and so forth that can be utilized jointly across the forces and across all domains. But to do this also requires the sharing of other types of resources, cyber, and in this particular case here, electromagnetic spectrum. Now, the electromagnetic spectrum really does complicate this in a variety of ways, and that's because of the challenges you see here on the right. The electromagnetic environment is becoming inherently much more congested just because of the proliferation of RF devices that are out there, especially in urban environments. And that congestion, that interference from those types of devices becomes an issue that can affect, it can either degrade, in some cases even deny the operation of these communication and sensing systems. Maybe a little bit more insidious is contention, and that is when you have adversaries that are intentionally jamming, trying to, again, disrupt or deny the performance of these systems. And then there are even, I'd say even more difficult environments where there's area access and area denial, where just the turning on of an emission source is a problem, because it will reveal the presence of that entity, and therefore that person or that system may get targeted. Now, to address all this, we've looked very broadly at all of various quantum sensor technologies and how they may apply here. And quantum RF is very uniquely situated. Most importantly, and maybe from the starting point, is that the broad spectrum tuning capability of the quantum RF receiver and its inherent resistance to different types of interference means that it becomes, in some ways, the converged RF system that allows real spectrum awareness, true spectrum awareness across nearly the full electromagnetic spectrum. The physical size reduction in these devices also makes it very well suited for deployment on a variety of different platforms, both large and small, and that will result in a density of these types of devices out there that collectively will be providing much more accurate real-time assessment of how that environment is changing or evolving over time. And with that information and the ability to process in real time means that we can make better decisions. Our OODA cycles, right, or our ability to orient, to observe, orient, decide what we're going to do, and then take action improves. And with that means we can also move around in spectrum. And that movement in spectrum in these next generation systems can be very synergistic. It can be done among a number of different systems all at the same time moving around in spectrum to avoid the effects of interference that you might be experiencing, for example, in an urban environment. Some of that, as I said, might be due to congestion. Some of it may be due to multipath interference or active jamming. But if you're aware of that before you enter into those environments, if you can see that at distance, and it gives you time to reconfigure your systems to operate in better portions of the electromagnetic spectrum, well, then you avoid those problems. And that gives you the ability to maintain those links of communication, to maintain the integrity of those networks, and therefore to be able to carry out those operations more effectively and efficiently in spite of those issues. So with that, Paul,
Thank you.
Hand it back to Max to talk about ticker.
Thanks, William and Paul. So I'll just say, ticker is a next generation high performance frequency reference. We like to call it a clock. Frequency references are a fundamental part of our communications infrastructure. They would work with systems like SkyWire in order to essentially divide up the spectrum into smaller and smaller slices so it could be utilized more effectively, whereas SkyWire allows you to access a wide range of the electromagnetic spectrum for both communications and data. Ticker kind of divides up that spectrum and allows the more efficient use of that spectrum. So it's a part of our communications infrastructure, both in civilian and defense, and we expect these frequency references to enable new capabilities that we haven't even thought of yet. And the most exciting thing about Inflection is how we're tying multiple technologies together, SkyWire, Ticker, and SuperStack, in order to enable, call it quantum enable capabilities that we're not even really looking at yet in these areas in which the technologies can work together.
Max, there was a question that came in the chat, and I think applies both to the question of GPS denial and all spectrum operations, which is, does these services based upon optical atomic clocks require the entanglement between different clocks?
They do not, although that is the direction that it's going. So for call it quantum 2.0, call them the currently available quantum technologies, entanglement is not required in order to improve the performance of our GPS positioning and timing systems. That said, we do expect optical clocks, of which Ticker is the leading edge commercial optical clock. We do expect optical clocks to eventually enable entanglement across space-based assets to improve these systems exponentially.
Thank you. And Caitlin, maybe we can turn to you now to talk about the part that SuperStack has to play in this RF spectrum awareness and dominance.
Sure. So the capabilities that are enabled by our quantum sensors really give us a new kind of playground of features to leverage in the software layer. So for example, we've developed in collaboration with our QRF team novel techniques for real-time, low latency radio frequency signal characterization and processing, which are necessary for spectrum awareness and control in a broad array of environments and in order to act dynamically. So today we can show near instantaneous capabilities in our software layer to analyze a signal for several tasks, which include modulation detection, jamming detection and mitigation, signal quality assessment. And notably, our approach is applicable to both currently fielded classical radio frequency receivers as well as quantum radio frequency receivers. But you get that extra advantage from QRF's capabilities. But in the future, what we really see is a clear path towards the development of software layers, which more tightly integrate with our quantum devices in order to squeeze out just that much more performance in real time, and potentially enable entirely new protocols for resilient communication.
Thank you. We'll turn now to talk about the next area of threat, and that is one that really is at the forefront today, which is that of asymmetric drone threats. And so what we're seeing is the emergence of small, cheap, disposable drones, either used individually or used in swarms, both for surveillance purposes and also for targeting purposes. And we're seeing this to really devastating effect, for example, in Ukraine and in the Middle East. And the threat is most severe because the traditional technologies for detecting, whether it be aircraft or missiles, are simply unable to detect soon enough drone attacks and mitigate those attacks. And thus, we turn to alternative technologies like quantum for potential solutions to this threat. So I'll turn now to William again to talk about the part that quantum radio frequency sensors have to play in addressing this pressing issue.
Yeah, thank you, Paul. Yeah, the actual detection, and even the classification of a drone as a drone, right, and as a threat, it is very difficult. These are small systems. They can be individual. They can fly as swarms. They can move quickly. They can deliver effects in very non-traditional ways to take out targets. Anything we can do to detect them early, whether that means at greater distance, or to be able to process these signal returns faster, so we can determine what they are and how to respond, is a benefit. And SkyWire, because of its unique, very broad frequency tuning capability, can offer a sensing capability, right, that operates both at low frequencies and as well as high frequencies. And so in various kind of multi-static configurations, it's conceivable that the quantum RF receiver, one portion of that multi-static system, would be able to simultaneously pick up very long range, almost over the horizon kind of signals, early detection of swarms at a distance. And then as these become, as they move closer, and there's the ability to also switch to more line of sight methods for more accurate, more precisely tracking and classifying and even imaging these kinds of assets. And the quantum RF receiver is able to do this both simultaneously as well as sequentially, allowing a continuous detection, tracking, identification capability, adding time to this OODA cycle, giving us time to verily determine that this is a threat and time enough to react to that threat, to decide what you need to do.
Great, thank you, William. And Max, I'll turn to you now for comments around the role that clocks have to play here.
Yeah, absolutely. So what Ticker does, what next generation atomic clocks do, is they allow us to coordinate both advanced systems like SkyWire and conventional radar systems in this bistatic or multi-static way, so we can pick out individual drones, one-way drones that have explosives on them, or swarms of drones, so that we can target and destroy them and protect them from our defense assets. I like to think of it as like 3D goggles, using conventional radar or quantum, advanced quantum technologies like SkyWire, so that you can actually discriminate between drones in a swarm or individual drones in, say, a forest in a cluttered background. This is, a here and now technology. Essentially, it's an upgrade path for our currently deployed systems. So it's a relatively inexpensive way of actually enabling this capability on systems that are already out in the world and being used. And I'll just throw it to Caitlin, because I think quantum software has a great capability that ties SkyWire, Ticker, and all of our quantum technologies together to provide this capability.
Yeah, so broadly speaking, our software solutions include what we've deemed quantum-inspired AI. So these would be AI models that are performant on today's modern GPUs, but are designed using principles from quantum information with a focus on emerging QPUs, or quantum processing units. And one of the main advantages we're able to yield with these novel quantum-inspired models is unprecedented contextual understanding across long time series of data. So regarding asymmetric drone warfare, and building upon my previous comments regarding the real-time RF signal characterization capabilities we have, our quantum software efforts are really enabling an ultra-low latency downstream application capability on top of our quantum devices. So in particular, the precision capabilities of, for example, the QRF, combined with the low latency application layers and this unprecedented contextual understanding, is really key to enhancing the capabilities of devices like SkyWire to detect and track extremely small and agile drones, which requires high precision in both space and time.
Thank you. So turning now to the last threat area, space domain operations. Space is both important as a platform from which we deliver PNT, obviously from a GPS perspective, a resilient GPS perspective, but also with the vast increase in space-based assets, both military and commercial, the need for space domain awareness, the ability to understand the position, behavior, and movement of space-based assets. And we'll talk now a little bit about the threats that represents, but also the potential solutions that quantum can offer. So I'll turn, first of all, again, back to Max to talk about the role of optical atomic clocks in space.
So primarily what the clocks provide is the extension of the GPS capability beyond the current GPS satellite constellations. So if you're tracking assets, generally, if you're inside GPS, you can track them using two methods. You can use GPS, or you can use RF-based time of flight methods that William will probably talk about. If you start going beyond the GPS satellites, now your only capability is to establish new GPS-like capabilities, and this is very, very exciting in the cislunar space. Or you can use these clocks for radio beaconing, radio-based navigation capabilities. So what SkyWire, what Ticker in fact does is provide a precision clock frequency reference so that you can locate and track these assets very precisely in the areas in which you don't have conventional access to that tracking capability. And I'll just throw it over to William to talk about SkyWire.
Yeah, thanks, Max. You hit on some really important points there. Space is enormous. I mean, there's orbital space, which is very, very dense. It's cluttered in many ways with lots of debris and lots of spacecraft, and there's cislunar, which is growing. And cislunar is just an enormous volume of space that will become more and more important for commercial and defense purposes in the future. Being able to detect and track all of these is incredibly difficult. But the quantum RF receiver is, again, uniquely positioned here because it does tune so broadly. It can tune from hertz, theoretically out to terahertz in frequency. And that means it is hyperspectral. And so anything that emits an electromagnetic signal out there is conceivably detectable and trackable from any kind of a traditional communication emission to let's say a sensing emission from some of these platforms, to even this to the black body radiation, the heat signature of the target, to something that can be detected using this technology. Again, all within one single device. You don't have to have multiple receiver systems that operate with disparate types of antennas and receiver subsystems. All of this can be achieved with one single device across the full spectrum. And it is physically small, and so that means it can be deployed on virtually all assets, and large and small, in that domain. Again, creating a much denser, more accurate awareness of the spectrum that's out there, and the items, in this case, the objects and the spacecraft that are that in that environment. Sorry,
Caitlin, I'll hand to you for the software component here.
Sure. So similar to the challenge of drone detection, precision spectrum awareness is needed to tackle full spectrum tracking and detection in space, but even more so when fractions of a degree are translating into massive absolute positioning error. So I think everything that I've talked about so far is relevant to the solution, but one unique way that Quantum Software Division can aid in this problem and in this regard is our experience in optimization techniques. So we have expertise in both classical and quantum solution spaces with regard to optimization. So for example, here, one highly relevant application is the challenge of radar placement. So in such a massive and dynamic environment. So our optimization solutions would enable optimal radar positioning, maximizing efficiency and coverage over an increasingly congested and contested space domain.
And Max, I'm sure inertial sensing has an important part to play, especially in the context of your earlier comments about lack of GPS availability above the GPS constellation. So maybe you could talk to us a little bit about the role that Exact has to play there.
Absolutely. So, the concept, the field is called PNT, position, navigation, and timing. So if you combine our clock capabilities with our initial capabilities. You can put them on board systems that are beyond the axis of traditional GPS locating systems, and that actually enables a whole wide variety of missions, as big as navigating to our outer planets, Mars and beyond, and as simple as simply locating this expansive opportunity set that William referred to, known as cislunar. So essentially, putting inertial systems on board these on board these assets allows you to locate them without reliance on either Earth-based or deployed RF locating systems. One of the more nuanced but exciting things is if you are on a autonomous mission to, say, Mars, call it a space-based drone mission, and you are trying to get a lander on Mars, local systems have a really hard time discriminating between acceleration of the vehicle you're on and the gravitational potential of the planet that you're approaching. The systems we're developing in Inflection can actually discriminate between local accelerations and gravity to enable these type of precision landings in the future.
One question that came in the chat, and Max, I'll point this one to you, is do you foresee quantum PNT, again, position, navigation, and timing, enabling entirely new types of drone missions or applications that are impossible with current navigation systems?
Yeah, and this is a great one. So I just talked about space. Those new missions are possible because you can locally position both timing and inertial assets on board to enable navigation beyond the GPS constellation. But a little closer to home, there are environments on Earth in which GPS can't penetrate. A really great one is the ocean. Generally, we do not have access to GPS systems underneath the ocean, and autonomous underwater vehicles are a whole new class of drones, of autonomous vehicles that require precision positioning in order to do their job, both for commercial jobs, call it undersea cable maintenance, or for defense in our submarine fleet, that require onboard positioning that is truly and only enabled by these quantum inertial and timing solutions.
Great, thank you very much. So I think we've talked about a number of significant national security threats and the way in which quantum has a role to play in addressing them. Laura, a question for you. In your view, what's holding the US government back from going big, going kind of all in on quantum technology?
Yeah, two things. One, a significant enough disaster has not happened yet. As William mentioned, he talked about the OODA loop, but the creator of the OODA loop, Colonel Boyd, he was a brilliant Air Force strategist. He said bureaucracies don't change absent a large disaster. And I'm not okay with that. I think that's ridiculous. I mean, we have to be on the forefront here. We have to be proactive, not reactive. And you know, we have to change that mindset. I think that's happening to some degree because we're seeing the Chinese build up specifically over Taiwan. But then the bureaucracy piece has to follow. And we treat quantum in the government as an R&D issue, not as an acquisition issue. And it's this lack of awareness that quantum is here and now, and that if we don't work on this here and now, then in the future will not belong to us. China believes the future belongs to them, and we kind of think that it belongs to us because post World War II, the international world order has generally been built, with U.S. leading. There is a significant chance that all changes pretty soon in the future until we get our hands around these technologies. So what we really need is one person. We have an immigration czar, a border czar. We need a quantum czar. We need one person in the government, specifically DoD, who truly has the authorities, the resources, the budget to really drive these technologies into acquisition systems rather than pockets of research here and there where we're, a few million here and there. I mean, that's a lot of money to me personally. But when you're talking about a technology like this, it's a drop in the bucket when, compared to China spending anywhere from $4 to $15 billion on this technology. We've got a lot of catching up to do.
Thank you, Laura. It's very helpful. Just a question that came in the chat here, and maybe this will be a question for William. Do you consider weather effects, weather turbulence effects, temporally and spatially in the models of our systems?
In general, weather effects are a problem, in a lot of communication and sensing systems, for a variety of reasons. If you think about it from like an environmental perspective, or a hardening of these receiver systems to operate in those environments, I would say that the quantum RF receivers today that we have developed are highly integrated. The atomics, the micro optics, and electromagnetic components are integrated in such a way that it is inherently resilient to things like shock, like thermal fluctuations, pressure variations, and so forth, that might affect the performance of certain systems. The fact that they're also physically small means that when they are integrated onto different platforms, they don't have the same physical presence as, say, an antenna system might have on an aircraft or on say a large naval vessel. And so that also means that they're not going to be, they're not going to experience the same kinds of forces and deal with the same kind of issues that some of those systems might have. The ability also to operate across a broad range of frequencies means that if in certain, let's say, weather conditions, certain bands are not particularly good, because there's too much loss at those frequencies, the ability to move away from those difficult bands into bands that are more useful, usable under those conditions is something that a quantum RF receiver can offer. And I would say even in a space environment, right, where weather conditions might affect optical communications, ground to space and space to ground, the ability again to move to other frequencies to support all weather operation is something like a quantum RF receiver could do. And I would go as far as to say that when you look also at the physics of what's happening in the cells, and that there is also an inherent resistance to radiation, whether that be man-made or in natural radiation that may occur, the atoms can reconstitute themselves very quickly. So the recombination rates are fast, and that means that there's also an inherent resistance to those kinds of effects that maybe traditional systems wouldn't do so well with.
Right. There was another question for Laura, as you mentioned China in your comments just now. And the question was, is there concern around China's progress in quantum, whether it's their speed, the number of patents and the investment they're making that you mentioned, or opacity, simply us not knowing what they're doing and the progress they're making?
Yeah, absolute concern. I mean, they're moving with rapid pace, and they're pouring resources into it in a magnitude and scale we've just not seen before. Opacity, I don't really. I'll leave that to my former colleagues in the intelligence community to maybe they know, but there's so much out there published. I mean, a lot of this is not secret. It's just they're moving faster than we are. And look, I think the US is still in the lead in many respects in the quantum race. The problem is just how quickly they're closing the gap. And it's because they are 100% motivated. They don't have the same bureaucratic challenges. Certainly they have other bureaucratic challenges, but they have the ability to direct government resources in a way that we just aren't willing to do in the US, and sometimes for good reason. We don't want to be China to beat China, but we've got to figure out a way to have better industrial policy to enable technologies like this.
Thank you very much. Okay, I'll hand over now to Max to talk a little bit more about Ticker that we've mentioned many times, but now to give you more of a sense of what the product is about and the roadmap for the future.
Absolutely, thanks, Paul. So Ticker is our atomic clock, our optical atomic clock. By moving to the optical domain with these clocks, we essentially get a 10,000 time faster tick in our clocks relative to current microwave clock technologies. What that provides is improved performance and improved resilience to shock and vibration and temperature and all the things that William just talked about. That's basically essential to get these things out in the field. What that means to the user, which is really where the rubber meets the road, is that you get a higher performance system that is small enough that you can actually put it on vehicles And then in our next generation of clocks, Tigger Blade, small enough that you can put it on dismounted warfighters or people just carrying these things around. And that results in, with respect to positioning, higher performance positioning, with respect to holdover, you get access to these timing signals that are critical for communications and for data when somebody jams your GPS signal. But the thing I like to say is, GPS distributes time throughout the world. If you disrupt that time signal, systems fail. What these things do is provide access to local assured time, keep those systems up and running in the event that you have both an adversarial attack or you have an innocuous attack just because you are operating in a tunnel or under the sea if you're a submariner, or if you're in space, your Space Force, and you're beyond the GPS constellation. It provides a local assured high performance time and frequency reference that you can use to keep all of your systems up and running in the event that you don't have access to those signals via GPS. Thanks, Paul.
Thank you, Max. And William, now to you for an overview of SkyWire in a bit more detail.
Yeah, thank you, Paul. I'd like to start with that picture there of that cell that's sitting right beside that quarter. This is a rendition of something that we've actually built. We built 1 cubic centimeter cells that are integrated with micro-optical and electromagnetic components that allow us to actually tune these devices across the full electromagnetic spectrum. These are one size cells. They don't change the function of the frequency of the wavelength that's used by devices for communications or sensing. It is one cell. They themselves are very sensitive, and they can be tessellated into arrays, for a variety of purposes, including for phased array operation, to do digital beamforming, to do interference mitigation, and so forth. They can also be tessellated into MIMO arrays and support MIMO applications. They're, again, very versatile. And in those arrays, right, there's huge advantage. There's obviously the direction finding capability that you derive from that. There's the geometric gain for improved overall sensitivity of the systems and therefore long range performance. They're also inherently low power. It doesn't take a lot of power to actually excite the atoms into these states in order to turn them into little receiver systems. They're, as I said to you, very broadly tunable, theoretically from hertz to terahertz. Now, we typically, in our labs and in the live demonstrations we've done in the field with these systems, tune from hundreds of kilohertz out to, in excess of 40 gigahertz and beyond. And so, again, very versatile, very unique among receiver systems. And as I was mentioned earlier, inherently robust against jamming. And all the other forms of interference or circumstances that might degrade traditional receiver systems. Key applications now that based on the engagement we've had with a large number of companies, both on the commercial and the defense side, and directly with the government, are things like signal intelligence, electronic warfare, communications. We've touched on this a little bit. There's also multi-static radar applications where, again, as a receive-only capability today, it lends itself very well to that, where you might have bistatic or multi-static systems where this would be the receive system. And again, the physical size reduction that it provides is dramatic. And one thing that I like to remind folks about is that when you do see physical size reduction like this on the array side, with potential improvements in overall sensitivity performance, it also means that you can drop the power on the emission systems, and that makes them inherently more LPI and LPD. And these are things that the defense community is very interested in. Sensor integration for broad spectrum utilization. Again, physical size reduction means that these will proliferate on multiple platforms, giving all platforms, even small platforms that previously were incapable of hosting, let's say, HF detection or operation below HF, could now do that. Small UAVs to small sats can now operate at very low frequencies where they could not have done before. And again, the Lego nature, if you will, this very modular design allows us to create all sorts of array structures, not only planar array, but even conformal. They can be used on various types of aircraft, around the fuselages, and again, even on small drone systems that previously would not have been able to host receive capability like this.
Great. Thank you very much, William. And Caitlin, over to you to talk a little bit more about the quantum software platform and application set.
Sure. So the Quantum Software Division has a wide array of offerings in both the classical and the quantum solution spaces. So what I really wanted to touch on again is some of the key specific ways that we are enabling a quantum future for defense. So the first is Sapient, which I mentioned earlier. This is our award-winning framework for fusing multimodal sensing devices, whether classical or quantum, in order to mitigate the effects of adversarial actions via, for example, GPS denial or spoofing, in order to ultimately enable reliable and robust PNT. And I would like to note that Sapient took first place in the Army's X-Tech Scalable AI Challenge this past year. And so we're really looking forward to future shareable demonstrations with our quantum sensors. And the next is Tactical, which represents a transformative application of quantum-inspired machine learning techniques, which are enabling unprecedented contextual awareness in both the time and space domain on the battlefield. So in the context of mission planning, and as you can see in the little image below, Tactical leverages our novel quantum-inspired models and our enhanced contextual awareness in order to enable just right visualization of the battlefield, as well as a state-of-the-art course of action analytics at varying levels of battlefield resolution. And then lastly, as I had mentioned previously, I'd like to highlight our collaboration with our QRF colleagues, where we have developed these state-of-the-art techniques for the real-time radio frequency signal processing that are applicable to conventional RF receivers, but really unlock the potential of QRF in the application space. And so we have downstream task demonstrations, which include modulation classification, a discussion of jamming detection and mitigation, general spectrum awareness. And so we'd be happy for the community to read a bit about our approach and our outlook on tightly coupled design for quantum sensing devices in the archive post shown on the screen.
Thank you very much. So in the final few minutes here, I think we'll kind of reflect on a quote from the Defense Innovation Board report from just a couple of weeks ago, in which they say the Pentagon needs to rapidly accelerate entry for non-traditional solutions, meaning outside of the traditional defense prime universe, that bring fresh ambition and ideas to compete. And Laura, maybe a question for you. How do you think the new administration and DoD appointments will impact the ability for companies like Inflection to leverage the DoD, both to have productive relationships with the Defense Department, but also the DoD as a pathway to larger commercial markets?
Yeah, I mean, by all indicators, it's all systems go, and ready to truly get a pipeline of non-traditional companies in there and working quickly. But let's not fool ourselves. U.S. government's a pretty big, hefty entity, and despite sometimes best efforts, it takes a little while to move the ship. But look, there's always been really smart, motivated, eager people in the government. And I think that they're probably going to be a bit more empowered at this point to get solutions like this into the pipeline to solve real problems to keep us all safe.
Fantastic. And I'll just share a kind of a short subset of the defense community partners that Inflection has worked with in the US, the UK, Australia, and beyond. We are a very active member of the ecosystem. Look forward to continuing to work with the names here on the slide and many others beyond. So we'll go now to Q&A. There were a few questions that came in. I think we have a couple of minutes to address them. And the first of them, maybe Max, I'll point this one to you. Do you expect GPS-free navigation backups to be also used in commercial aircraft, ships, and other platforms? We've talked about how they're used in a military context, but what are your views commercially?
Absolutely. GPS backups will be pervasive. They'll start with higher value, safety critical systems, but they will move down to the systems that we use every single day. And I'll just give one very specific example. Over Eastern Europe, over the Middle East, there's been a proliferation of spoofing attacks in which the positioning of aircraft is essentially shifted from where the expected position is. or the true position of that aircraft is. So it is a dangerous situation in which our adversaries are actually manipulating the GPS signal in order to cause confusion. And what I expect to see happen is federal agencies like the FAA to start to require anti-spoofing capabilities to be integrated into these aircraft. It'll be a combination of a hardware solution and a software solution that can very rapidly detect these spoofing attacks and correct for them using local sources of truth. And we think that our technology is a great fit for this particular commercial safety application.
And Max, the next question actually also for you. You've talked about inertial sensors, exact. And the question is, are you talking about quantum accelerometers or gyroscopes, or are you talking about both of those in some kind of combination?
Both. So both accelerometers and gyroscopes are required for a full inertial navigation solution, a GPS-free navigation solution. And we at Inflection are working on both of those technologies, both rotational and linear inertial sensors, as well as gravitational and gravity gradiometer sensors, which are a form of inertial sensor that is tuned for detecting changes in the gravitational field.
And then I think perhaps the last question here, and Max, actually for you again, what are the major challenges of atomic clock-based constellations in space? Is it the engineering challenge to minimize narrow line-width lasers, or the long lifetime vacuum chambers without requiring re-vacuum? I mean, I think fundamentally the question of putting quantum technology in space, the answer to what's hard about it is everything, but maybe you can talk about some of the specifics.
Just, Inflection has a long legacy of putting systems in space. We are a part of the Cold Atom Laboratory, in which we deployed systems on the International Space Station, and we've been a part of 2 refresh missions for that particular application, which is a NASA mission. William touched on some of the challenges of QRF systems in space, and he actually pointed out that the core atoms that actually do our sensing of all of our systems are relatively immune to some of the traditional challenges of, say, metallic-based systems in space, in which electromagnetic radiation causes fundamental challenges with all of these deployed systems. So we, as a technology, face the same challenges of any other traditional technology in deploying them in space. They have to go into rockets. There's a lot of shock and vibe. If you're shaking these things around and you don't appropriately harden the systems, they will break and then they won't do their job. And that's what we're actually going through with a contract with Space Force, which is to look at designs to harden our optical atomic clocks for future deployment missions as an upgrade path for GPS, as well as these independent applications. And I'll say that redesign effort that we're applying specifically to clocks, which have a very clear use case for space, will flow down through our other technologies and allow those to be hardened rapidly for these emerging applications in space.
Thanks very much, Max. And just in the last couple of seconds here, if you'd like to learn more about anything that we've talked about today, please feel free to contact us, either contact William, Max, or Caitlin directly, or go to our website and fill out the form, and we'd be happy to talk to you about anything that we've covered today in more detail. So with that, thank you very much for joining us. Thank you very much for your time. Thank you to my fellow panelists and to Laura, our advisor, for a fascinating discussion. We look forward to seeing you again on future Inflection webinars.